Good afternoon. Today we have a second lecture in statistics, and today we need to discuss methods of inferential statistics. I want to remind you that there are different types of statistics: descriptive statistics, correlational statistics, and inferential statistics. Previous lecture we discussed descriptive statistics method, which are used to organize, summarize, and describe data we collect during our study. Today we will talk about inferential statistics. Uh, Inferential statistics methods are used to generalize information, and we will discuss statistics which describes relationship between variables, which is called correlational statistics. Inferential statistics can be used to prove or disprove theories, determine association between variables, and determine if findings are significant and whether or not we can generalize from our sample to the entire population. We make inferences about a phenomenon by using methods of inferential statistics. There are some different methods, such as hypothesis testing and correlation. We use inferential statistics method to prove or disprove theories, to study associations between phenomena, to study if sample relates to the larger population. Examples are using different diets and health for the patients, for the persons. Today we will cover next questions. What is hypothesis testing? Null and alternative hypothesis, statistical tests, p-value, in hypothesis testing, significance level, power and sample size, and correlation and regression. In prior lecture, we introduced some terms. Let's revise these terms. Population, all possible values in a variable we are interested in. Sample is a portion of the population, so this is a small group driven from the population. Statistical inference. We use statistical inference to generalize from a sample to a population with a calculated degree of certainty. Parameter. This is a characteristics of population. I want to remind you, if we use Greek letters, it concerns to the whole population. If we use Latin letters, it concerns to the sample. And if we are talking about the sample, we are talking about statistics. We calculate statistics from data in the sample, and we denote these statistics by using Latin letters. There are two forms of statistical inferences: hypothesis testing and estimation. The type of data defines statistics used for analysis. So this is the first step for each statistical analysis is to understand which type of variable should be analyzed. According to these types, we should use parametric tests or non-parametric tests. We use parametric test for continuous data normally distributed, and we use non-parametric test for continuous data non-normally distributed, for categorical or ordinal data. Different types of variables were discussed during previous lecture. Now let's start with hypothesis and hypothesis testing. In statistics, two types of hypotheses are distinct. First of all, let's look at the definition. Hypothesis. Hypothesis is a statement expressing an opinion based on incomplete evidence. A tentative insight into the natural world, a concept that is not yet verified, but its truth would explain certain facts or phenomena. If we're interested in some phenomena or in some fact, we need to convert the research question to null and alternative hypothesis. The null hypothesis, we use HO is a claim of no difference in the population. Alternative hypothesis is the opposite hypothesis to the null one, and we denote it as HA or H1, claims HO is false. So the first step in hypothesis testing is to set up null and alternative hypothesis in the fact or in the about the fact or about the phenomena we are interested in. Then, after we set up null hypothesis and alternative hypothesis, both these hypotheses are set up together. It is impossible to set up one hypothesis only. It is necessary to set up both hypotheses, null and alternative. Then we need to collect data and seek evidence against null hypothesis as a way of bolstering alternative hypothesis. This method is called as deduction method. So if we can prove that there is evidence against H null, so we can bolster HA. Hypothesis testing is also called significance testing. Tests a claim about a parameter using evidence or data in a sample. The technique is introduced by considering a z-test. The procedure is broken into some steps. Each element of the procedure must be understood. So, the general goal of a hypothesis test is to rule out chance as a plausible explanation for the results from a research study. Hypothesis testing is a technique to help determine whether a specific treatment has an effect on the individuals in a population. The hypothesis test is used to evaluate the results from a research study in which a sample is selected from the population. The treatment is administered to the sample. After treatment, the individuals in the sample are measured. So, the main purpose we use hypothesis testing. We use hypothesis testing in the case if we need to compare different populations or different samples. And the goal of this comparison is to understand, is there differences or there is no differences before and after the treatment, for example, if we are talking about medicine. So we know the population before treatment, then we apply some treatment or we apply some drugs to the sample, and we have a sample after the treatment. If the individuals in the sample are noticeably different from the individuals in the original population, we have evidence that the treatment has an effect. However, it is also possible that the difference between the sample and the population is simply sampling error. So, we have two different populations, known original population And after the treatment, we have unknown treated population. We take sample from the above population and have sample and treated sample, and use these samples for comparison by using hypothesis testing. The purpose of a hypothesis test is to decide between two explanations. The difference between the sample and the population can be explained by sampling error. There does not appear to be a treatment effect. The difference between the sample and the population is too large to be explained by sampling error. There does appear to be a treatment effect. The distribution at this slide, you see the distribution of sample means if the null hypothesis is true. So the set of potential samples is divided into those that are likely to be obtained and those that are very unlikely to be obtained if the null hypothesis is true. We use this graph to understand which hypothesis should be accepted. Can we reject null hypothesis, or there is no evidence to reject null hypothesis? At this slide, you see 4 hypothesis testing steps. The first step always is to set up null and alternative hypothesis. Then we need to test statistics. So we need to calculate it first. Then we need to estimate p-value and interpret this p-value. And optionally, we can estimate significance level and make our conclusions. Let's talk about each of these steps. Step 1, state the hypothesis and select an alpha level. The null hypothesis, HO, always states that the treatment has no effect, no change, no difference. According to the null hypothesis, the population mean after treatment is the same as it was before treatment. The alpha level establish criteria or cutoff for making a decision about the null hypothesis. The alpha level also determines the risk of a type 1 error. At this slide, you see the locations of the critical region boundaries for 3 different levels of significance. If we use alpha level equals to 0.05, the critical region is from minus 1.96 till plus 1.996. Then if we state alpha level equals to 0.01, the range of rejection varies from minus 2.5 till plus 2.5. And if we use alpha level equals to 0.001, the region for rejection region varies from minus 3.3 till plus 3.3. So we need to, after we set up alpha level, we need to locate the critical region. The critical or rejection region consists of outcomes that are very unlikely to occur if the null hypothesis is true. What is the critical region is defined by sample means that are almost impossible to obtain if the treatment has no effect. The statement almost impossible means that these samples have a probability p that is less than the alpha level. At this slide, you see ranges which can be used to reject null hypothesis or to fail reject null hypothesis. The critical regions, their unlikely outcomes for alpha equals to 0.055 is shown at this slide. The critical region varies from minus 1.9 till plus 1.9, and if the mean is located inside this critical region, we can make our decision. We fail to reject null hypothesis. If the mean or middle value is located outside this critical region, we make our conclusion that there is no enough evidence to reject null hypothesis. Values of the test statistics for which we reject the null hypothesis in favor of the alternative hypothesis is called as rejection region. And in this slide you see two parts of rejection regions, and the cut points for these parts is z equals minus and plus 1.96. Then, after we construct rejection region, we need to calculate the test statistics, so-called z-score. Test statistics, this is a quantity based on a sample data and null hypothesis used to test between null and alternative hypothesis. The test statistics forms a ratio comparing the obtained difference between the sample mean and the hypothesized population mean versus the amount of difference we would expect without any treatment effect, the standard error. After we calculate z-score, a large value of the test statistic shows that the obtained mean difference is more than would be expected if there is no treatment effect. If it is large enough to be in the critical region, we conclude that the difference is significant or that the treatment has a significant effect. In this case, we reject the null hypothesis. If the mean difference is relatively small, then the test statistics will have a low value. In this case, we conclude that evidence from the sample is not sufficient and the decision is failed to reject the null hypothesis. At this slide, you see an explanation of hypothesis testing. So we have the practical example with the structure of a research study to determine whether prenatal alcohol affects birth weight. A sample is selected from the original population and is given alcohol. The question is, what would happen if the entire population were given alcohol? The treated sample provides information about the unknown treated population. So we are in this example, we are interested does alcohol affect birth weight or not? So the null hypothesis for this example is alcohol. There is no differences in birth weight between population without alcohol and population with alcohol. And alternative hypothesis, we set up alternative hypothesis or opposite to the null one. There is differences between prenatal alcohol population, between population without prenatal alcohol and between population with prenatal alcohol. For comparison, we need to look at the birth weight. Let's talk about errors in hypothesis testing. Just because the sample mean is different from the original population mean does not necessarily indicate that the treatment has caused a change. You should recall that there usually is some discrepancy between a sample mean and the population mean simply as a result of sampling error. Because the hypothesis test relies on sample data and because sample data are not completely reliable, there is always the risk that the misleading data will cause the hypothesis test to reach a wrong conclusion. Two types of error are possible. At this slide, you see these two types of errors in hypothesis tests. Two types of errors may occur when deciding whether to reject HO based on the statistic value. Type 1 error, we denote as usual, we denote it as alpha. The first type means that we reject HO, then it is true. And type 2 error, we denote it as beta. We don't reject HO, then it is false. So from this table, we have two wrong conclusions with type 1 error and with type 2 error. The goal in hypothesis testing is to keep alpha and beta reasonably small. The power of a hypothesis test is defined as the probability that the test will reject null hypothesis when the treatment does have an effect. The power of a test depends on a variety of factors, including the size of the treatment effect and the size of the sample. There are two types of tests which can be used in hypothesis testing according to the direction. Then a research study predicts a specific direction for the treatment effect. If we are interested in increase or decrease, it is possible to incorporate the directional prediction into the hypothesis test. The result is called as directional test or a one-tailed test, one-sided test. A directional test includes the directional prediction in the statement of the hypothesis and in the location of the critical region. If we aren't interested in the direction, but we are interested in the difference between populations, we need to compare only. In this case, we should use unidirectional test or two-tailed test or two-sided test. But if we are interested in direction, we should use one-tailed or one-sided test. For example, if the original population has a mean of mu equals to 80 and the treatment is predicted to increase the scores, then the null hypothesis would state that after treatment there is no increase. So in the directional test, for the null hypothesis, we should use mathematical size or mathematical signs great or less than. If we use unidirectional test, we should use equation with equal sign only. So for unidirectional test, we should type mu equals 280. For directional test, we should type mu less or equal 80. There is no increase. In this case, the entire critical region would be located in the right-hand tail of a distribution because larger values for m would demonstrate that there is an increase and would tend to reject the null hypothesis. If we use unidirectional test, both critical regions should be used in the hypothesis testing. Let's look at the example. The task is the next one. In the 70s, 29-year-old man had a mean mu body weight of 170 pounds. Standard deviation sigma was 40 pounds. We test whether mean body weight in the population now differs. So we need to understand is there differences in the body weight between the same population with the same with the same age, or there is no differences. So null hypothesis. Let's state null hypothesis. The body weight equals to 170 pounds. So there is no difference in the population in the 70s and 17s and nowadays. The alternative hypothesis is the next one. Mu is greater than 170, or mu not equal 170. So if we are interested in direction, we should type mathematical sign great or less. If we aren't interested in direction and we need to understand only difference only, it doesn't matter with direction. So we should type mu not equal 170. So for the first alternative hypothesis, we should use one-sided test or one-tailed test. For the second alternative hypothesis, we should use two-sided test or two-tailed test. So this is an example of one sample test of a mean, then sigma is known. Use the statistics to test the problem. So there is special formula how to calculate the statistics, but you don't need to memorize these formulas because nowadays we should use special statistical applications which calculate these Z statistics and gives correct value. So the main purpose is to interpret this value correct. At this slide, we calculate Z statistics for two different samples. If we found a sample mean of 173, then z statistics equals to 0.6. If we use statistical software, we only get the z value, and it is the same 0.7. So you don't need to make these calculations manually. Use the appropriate statistical applications. In our course, we will use medical statistics software. That's why I asked you to install medical statistics at your computers, because you should solve all the practical questions by using this software. A computer automatically calculates all statistics you need to make your statistical conclusions, but your goal is to interpret these values correct. And if we found a sample mean of 185, then z statistics equals to 3. So at this slide you see an explanation of this example. So we know that population mean in 1917s body weight equals to 170 pounds. Nowadays we draw different simple random samples, and the size of these samples is the same and equals to 64 persons, and we calculate mean in each sample, and for example we get mean for body weight equals to 173. For the next sample, we calculate sample mean and it equals to 185 pounds. For next sample, with the same sample size equals to 64 persons, we get mean in weight equals 174, and so on. So we can make graph of the distribution of for all the possible means in body weight, and the graph shown at this slide and log distribution of this graph is the normal one. And look at the mean. For this graph, the mean equals to 170 pounds. Let's talk about p-value. We can make a point estimate and a confidence interval estimate. What is a p-value? P-value is a significant value, and we use it as an arbitrary number. P-value does not measure the strength of association. It measures the likelihood that the observed estimate is due to random sampling error. If we get p-value less than 0.05, this means, by conversion, an indication of statistical significance. The p-value answers the question, what is the probability of the observed test statistics, or the more extreme than HO is true? How to interpret p-value? P-value answers the question, what is the probability of the observed test statistics, then HO is true. Thus, smaller and smaller p-values provide stronger and stronger evidence against HO. Small p-value means strong evidence. Let's look at the conversions. If we get a p-value greater than 0.1, we can make our conclusion there is no significant evidence against HO. If the p-value varies from 0.5 and 0.1, our conclusion is marginally significant evidence. If p-value varies from 0.01 till 0.05, our conclusion is significant evidence against HO. And there are highly significant evidence against HO. We can make this conclusion if p-value is less or equal 0.01. Examples: if statistical software, if the p-value equals to 0.27, there is no significant evidence against HO. If p-value equals to 0.01, there is highly significant evidence against HO. Alpha level, let alpha probability of erroneously rejecting HO. Set a threshold. There are three thresholds for alpha: 0.1, 0.05, and 0.001. But we can get any alpha level, but the most popular are these three. Then the rule is the next one. We need to reject HO, then p-value is less or equal alpha. Retain HO, then p-value is greater than alpha. Example, if we set alpha equals to 0.1 and p-value is 0.27, we need to retain H0, and we need to make our conclusion there is no enough evidence to reject HO. If we set alpha 0.01 and p-value equals to 0.001, there is enough evidence to reject null hypothesis. If we reject a null hypothesis, we conclude that there is enough evidence to infer that the alternative hypothesis is true. If we do not reject the null hypothesis, we conclude that there is not enough statistical evidence to infer that the alternative hypothesis is true. The alternative hypothesis is the more important one. It represents what we are investigating. So look attentively to this slide. So we are interested in alternative hypothesis. So it is important to find evidence to reject null hypothesis, and in this case, due to the deduction method, if we reject null hypothesis, we accept alternative hypothesis. We reject null hypothesis in favor of alternative hypothesis. Now let's repeat steps of hypothesis testing again. So first we need to describe in words the population characteristics about which hypotheses are to be tested. So we need to state null hypothesis, and we need to state the alternative hypothesis. Then Then we need to find out the test statistics to be used. Then we need to plot the rejection region. Is it upper, low, or two-tail test? We need to find out correct method of hypothesis testing. We need to determine the critical value associated with alpha, the level of significance of the test. Then we need to compute all quantities in the test statistics and compute the test statistics itself by using statistical applications. Then we need to state the conclusions, that is, decide whether to reject the null hypothesis HO or fail to reject the null hypothesis. The conclusion depends on the level of significance of the test. Also, remember to state your result in the context of the specific problem. It is very important to state our result in the context of the specific problem. All the previous steps we should make by using statistical software. Only first step is manual step. So if we state null hypothesis and state the alternative hypothesis, we should type this hypothesis. Then all intermediate steps should be done by using special software. And the last step, we need to state the conclusion, to make our conclusion in the context of the practical task. It is very important. So this is explanation how to apply one sample z-test to the practical questions, but this is mathematical way. So the first step is to state hypothesis statements, to state null and alternative hypothesis. It is possible, there is only one way to state null hypothesis. Then we need to make our statement there is no differences between two samples or between two populations. We can make this to denote these differences by using equal sign. There is no differences, so this means that we should use equal sign. And there are three possible alternative hypotheses. If we state that there is no difference, there is difference, and we aren't interested in the direction, we should use two-sided or two-tailed test. In this case, we should type alternative hypothesis as mean from one population doesn't equal to the mean from another population. Then, if we are interested in the direction, we should use one-sided test, or left-sided or right-sided, according to the side we are interested in. We should use or less than sign or greater than sign. For less than sign, we should use left-sided. For greater than sign, we should use right-sided. Then we need to calculate test statistics by using software, so we don't need to memorize these big formulas and to understand them. With the Z statistics value, computer calculates also p-value. And the main is to interpret this p-value correct and to estimate significant statement. If samples of size less than 30 are taken from normally distributed population, a t-test may be used to test the difference between the population means mu1 and mu2. So according to the type of distribution, we should use or parametric or non-parametric test. If we have normally distributed population, we should use method which is called students t-test. Assumes normally distributed assumes we have normally distributed continuous data. A lot of medical characteristics are distributed normally. Because of this, the normal distribution is very important in the nature and in the medical practice. Such as examples are body weight or body height and so on. Another type of tests we can apply to in the hypothesis testing is called as paired t-test. We use it uses the change before and after intervention in a single individual or in the group of individuals before and after the intervention or before and after the treatment. For example, we should use T-students test if we compare two different independent samples. Independent samples means that all persons from one sample are different from the persons from another sample. Dependent samples mean that we use the same persons or same objects before and after the intervention, before and after the treatment. So paired t-tests reduces the degree of variability between the groups, and given the same number of patients has greater power to detect a difference between groups. At this graph you see explanation of how to use paired t-test. We have scale with hormone level and two time points, pre-test levels and post-test levels. But we use the same objects to measure hormone levels before and after the intervention. In this example, we use paired t-tests. One more method of hypothesis testing is analysis of variance. It is used to determine if two or more samples are from the same population or not. If two samples, if we have two samples, we should use t-test. If we have more than two samples, three or more samples, we should use analysis of variance. If it appears they are not from the same population, can't tell which sample is different. So by using analysis of variance, we can only answer question, is this is all these samples from the same population or different? And after we make analysis of variance, we need to do pairwise test to understand which sample is different from another. Non-parametric tests. So if we need to analyze variables with non-normal distribution, we should use another methods which are called non-parametric tests. So for non-parametric tests, we can use methods of testing proportions, so-called chi-squared test or Fisher exact test. To test ordinal, we use non-parametric tests to test ordinal variables. To test ordinal variables, Mann-Whitney test is used, or Kruskal-Wallis one-way ANOVA test is used. If I have ordinal paired variables, we should use sign test or Wilkinson rank sum test. So it is very important to understand type of variable which should be analyzed and type of distribution. According to these two characteristics, we should apply appropriate methods. As usual in statistical software, you need only choose correct variable type and choose correct distribution, and computer automatically will choose correct statistical test. After you get intermediate results, the main is to make conclusions correct. So, non-parametric tests used for categorical, ordinal, or non-normally distributed continuous data may check both parametric and non-parametric tests to check for congruity. Most non-parametric tests are based on ranks or other non-value related methods. Pearson's or chi-square test used to compare observed proportions of an event compared to expected, used with nominal data. Examples of nominal data, for example, better, worse, dead, alive, and so on, for binary data. If there is a substantial difference between observed and expected, then it is likely that the null hypothesis is rejected, often presented graphically as a 2-by-2 table. At this slide you see formula, how to calculate chi-squared value, but you don't need to memorize it because computer automatically calculate this chi-squared value. Chi-squared test is not applicable in small samples. If fewer than 5 observations per cell, we should use Fisher exact test, not chi-squared. Then if we need to study, if we need to understand relationship between two or more variables, we should carry out correlational analysis. Correlational analysis or correlation is the association between two or more variables. For example, correlation assesses the linear relationship between two variables. For example, we are interested, is there association between person's height and person's weight? We are interested, is there a relationship or not? To understand and to prove that there is a relationship between height and weight, we need to carry out correlational analysis. Correlational analysis consists of two steps. The first step is to calculate correlation coefficient. We denote a correlation coefficient by using Latin letter R. and we use correlation coefficient to estimate strength of this association between two variables such as height and weight. And there is special formula to calculate correlation coefficient, but in the statistical software we get value of R which varies from -1 till +1. According to the range in which this R appear, we can make our conclusions about strength of the association. And in this slide you see these conclusions. So if we are talking about correlation coefficient, strength of the correlation coefficient, we need to look at the absolute value for correlation coefficient. Correlation coefficient varies from -1 till 1. If we are talking about absolute value, this means that we need to ignore sign. And in this case, the absolute value for R varies from 0 till 1. According to the ranges, we can make our conclusions. If R ranges or values from 0 till 0.2, we need to make our conclusion there is lack of association, lack of relationship between variables we are interested in. If it varies from 0.2 till 0.4, it is low, possible important association. Then, if it varies from 0.4 till 0.6, there is moderate association between variables. From 0.6 till 0.8, high correlation, and if correlation coefficient varies from 0.8 till 1, there is very high correlation. But this is explanation of absolute value. So absolute value influence at the strength of correlation. But then correlation coefficient can be positive or negative. So according to the sign, we can make our conclusion about association, about the direction. Look, for example, this graph shows positive sign for correlation coefficient, and look, we have two variables. For example, level of hemoglobin for vertical axis and fasting blood level of fasting blood glucose in horizontal axis. Points are the values for both these variables. We have two variables, and we denote all points at this graph. So it is possible to understand this that all points goes upward. This is inherent to the positive correlation coefficient. The second step in correlation analysis, then if we calculate correlation coefficient, the second step is to make correlation graph. Correlation graph consists of dots of couple of values. Each point depicts this is point with coordinates for one variable and for another variable. So the correlation graph is the scatter plot graph. And according to the allocation of these points, we can make our conclusion about association between two variables. At these graphs, you see two different correlations between two variables. In the A graph, correlation coefficient equals to 1, the maximum correlation coefficient. Look at this graph. All points goes upward and all points are allocated at some invisible straight line. At the B graph, you see a correlation graph for correlation coefficient equals to -1. All points are allocated at the invisible straight line, but all points go downwards. So this is example for perfect correlation. Perfect correlation means that at these examples we have a linear relationship between two variables, or functional linear relationship. Next graph. For example, we need to understand, is there association between age and systolic blood pressure all measures are depicted at this graph. So look, there are a lot of points, but we can't check any trend at this correlation graph. And if we calculate correlation coefficient, it equals to 0. Look at the this scatter plot graph and look at the correlation coefficient. If we get correlation coefficient equals to 0, this means that there is no association between age and systolic blood pressure. And due to the graph, we can make our conclusion. It is scatter plot graph, so we can make our conclusion from graph also, and we can confirm by using value of correlation coefficient. Correlation coefficient equals to 0, and we have scatter plot graph for this example. There is lack of correlation between age and systolic blood pressure during daytime. Two more graphs are shown at this slide. E graph is scatter plot graph for correlation coefficient -0.5. Look at the points. It is possible to understand that all points go downwards. At the F graph, all points go upward. Look at the correlation coefficient for F graph. It equals to 0.07. So if we get negative sign, this means negative correlation. For positive sign, we have positive correlation, negative and positive correlation. According to the graph, we can depict this correlation by using different direction. Negative correlation means if one variable goes for positive sign, if one variable increases, this effect second one also increases. If one variable decreases, it effect second one also decreases. This is conclusion for the positive correlation. For negative correlation, variables go in the opposite direction. That means if one variable increases, it affects second variable to decrease, or if one variable decreases, it affects the second one increases. For positive sign, both variables change the same direction. For negative sign, they change the opposite direction. And in the graph, we see different slope for the points. Regression. What is regression? Regression is the mathematical way to represent association, mathematical way to represent association or represent correlation. Regression based on fitting a line to data provides a regression coefficient, which is the slope of the line. So if we make regression analysis, so we need to substitute correlation by using mathematical equations. The mathematical equation for the line is y equals to ax plus b. We use regression or regression analysis to predict a dependent variable's value based on the value of an independent variable. So if we can type the mathematical equation, so we can predict value for variable. Regression is very helpful in analysis of height and weight. For a known weight, one can predict for known height, one can predict weight. And regression is much more useful than correlation because of prediction. Allows prediction of values of y rather than just whether there is a relationship between two variables. But correlation, so regression is the mathematical way to represent correlation. But correlation is the most popular, most important association between variables in the nature. A lot of phenomena we can describe by using correlation, because mathematical, the correlation is the more sophisticated association than the mathematical association. There are different types of regression. The simplest type of regression is linear, and because of which we, as usual, this type of regression is used the most often. Linear uses continuous data to predict and continuous data outcome. Logistic uses continuous data to predict probability of a dichotomic outcome. Poisson regression, time between rare events, and Cox proportional hazards regression. We use it to estimate survival in survival analysis, to estimate survival. Multiple regression models. If we have more than two variables, we should use multiple regression models. We use multiple regression models to determine the association between two variables while controlling for the values of others. Examples are uterine fibroids, both age and race impact the incidence of fibroids. Multiple regression allows one to test the impact of age on the incidence while controlling for race and all other factors. In published papers, the multivariable models are more powerful than univariable models and take precedence. Therefore, the discount the univariable model as it does not control for confounding variables. For example, look at the examples. Coronary disease is potentially affected by age, smoking status, gender, and many other factors. But this type of association is very sophisticated, so we can simplify it by using correlation only. If assessing whether height is a factor, if it is significant in univariable analysis, but not on multivariable analysis. These are the factors confounded the analysis. Look at this table as an explanation, as a summary of statistical tests. So according to the different practical tasks, according to the different practical situations, we should use different statistical methods. We use correlation if we need to examine two continuous variables. In this case, we should use Pearson's correlation coefficient. There are different types of correlation coefficient. For normally distributed variables, we should use Pearson correlation coefficient. For non-normal, we should use Spearman correlation coefficient. Examples are, if we are interested to answer the question, for example, are blood pressure and weight correlated? So you should collect data about blood pressure and weight. Then you need to input this data into medical statistics software and calculate correlation coefficient and make correlation graph. And then you should make your conclusion about association, about relationship between blood pressure and weight of the patients, of the persons. If you need to answer test, do normal weight from the group 1 patients have lower blood pressure than obese patients from group 2. You need to apply students T tests, and you need to calculate means from a continuous variable taken from 2 or more groups. To answer this question, you need to state two hypotheses first, null hypothesis and alternative hypothesis, and then test this hypothesis by using t-tests if the variable, both variables are normal distributed, or ANOVA test if variables are non-normal distributed. To answer question, for example, are obese individuals, obese versus or not obese, significantly more likely to have a stroke, you should use chi-square test because you are interested in two categorical variables. And you should use logistic regression for dichotomous variable as the outcome and answer the next question: does obesity predict stroke? Then controlling for other variables. So according to the different practical tasks, you should use different statistical methods, different statistical tests. We finish with our second lecture in statistics. And understanding basic statistical concepts is central to understanding the medical literature. Uh, it, it isn't important to understand the basis of the test or the underlying math, because nowadays we use statistical applications. But it is important to interpret these results correctly. And we need to know that a test should be used and how to interpret its results. Main is to correct interpretation of the results, because in the statistical applications you get values, and doctor should interpret these results correct. During our next practical classes, we should apply this theory to the practical tasks, to the practical situations. But before this practical classes, you need to install MedStat into your computers, because we need to use this software to solve statistical questions, and you need MedStat as a tool to make your individual assignment for CP2, control point 2. So we finish with this lecture, but actually it's just the beginning of in your understanding of statistical methods. Thank you for attention.